This lecture introduces the definite integral and some applications of definite integrations. First, we will talk about one of the fundamental theorems of calculus. It's a theorem about a continuous functions, right? If you have a functions f as the continuous functions on a closed interval from a to b, and big F is an antiderivative of f on the closed interval from a to b, then the integral of the functions f of x from the point a to point b is equals to big F of b minus big F of a. So this theorem is about an antiderivative functions, right, on a closed interval, and you can calculate the antiderivative functions on the closed interval using this formula right here, where big F is an antiderivative of f, and a and b are the endpoints of the closed interval from a to b. So as we remember earlier, when you talk about antiderivative of f, you have a integral of a function f of x dx. When you don't have any bounds from a to b, then you will come up with a big an antiderivative function of f of x and u plus c, right? Because you have different value for c that you can plug in depending on the initial value. But in this case, if you have bounds for your integrals f of x dx, bounds from a point A to a point B, and again, this functions here has to be continuous, then it will give you an actual value, big F of A minus big F of B minus big F of A. So this is the functions, right? Functions at a constant, and this is a value, an actual value. So it's actually equals to an actual value. And this is just a functions plus a constant. All right, so remember to distinguish between this is indefinite integral. And then this is definite integral. All right, we can talk about some rules for the integrations for the definite integral when you have bounds from a point A to a point B. First, switching bounds. So if you have an definite integral of functions f of x from a to b is the same as the negative integral of f of x from b to a. So if you switch the bounds from a to b to b to a, then you have to switch the sign of the definite integral. You can split the interval into two pieces or more than two pieces. So in this one, we're considering the functions from point A to B, then we can have a point C, right? This is A here, this is B here, and then you can have a point C in the middle of A and B, and you split this into two different intervals. Then the infinite integrals of the function f of x from A to C plus integrals from C to B equals to the integral of f of x from A to B. All right, and if the bounds are the same, then the integrals is 0. Okay. Then you can add or subtract two definite integrals, right? If you are taking the definite integrals of the two different functions on the same closed interval from A to B. So the definite integral of f of x plus or minus g of x from a to b is the same as the definite integral of f of x from a to b plus or minus the definite integral of g of x from a to b. And the last rule is you can, if you multiply a constant by a functions, then you can pull the constant k here out to the front, and you just need to evaluate this definite integral from a to b, and then you multiply this definite integral by k. All right, now let's do a couple of examples here. Example number 3, find the integrals, and you know this is the definite integrals because you have bounds, right, from -1 to 1. Again, this will be equals to big F of 1 minus big F of -1. So the first thing we need to do is we need to find the antiderivative of x squared. And we remember that antiderivative of x squared is x cubed over 3, right? And then you integrate it from -1 to 1. Then you just need to plug 1 into the function, antiderivative functions minus -1, 3. And then you will have 1/3 plus 1/3 is 2 over 3. All right. So then this is big F of 1, right? And this is big F of -1. And this is the antiderivative of x squared. All right, next example. You have functions, and then you need to find the definite integral. So first thing is you need to find the antiderivative of this function. So I want to rewrite this, right? X is 1/2. Square root of x is x to the 1/2. Then you can use the power rule in order to find the antiderivative of square root of x. So you would have x 1/2 plus 1 is 3/2, right? And divided by 3/2, so which means multiply to 2 over 3, but I divided by 3/2 first. Plus 3, antiderivative of s should be negative of cosine, because the derivative of cosine is negative s, negative sine, then negative of the antiderivative of negative cosine should be sine. And then this one here looks familiar, is the derivative of arctangent. Remember, the derivative of arctangent is 1 over 1 plus x squared. So that means the antiderivative of 1 over 1 plus x squared is the function's arctangent of x. All right, and then this functions here has multiplications. It doesn't work the way it so integrations, rules of integrals doesn't have any rules on the products or quotients, right? Functions. But then one thing that we can notice is we have sine of x squared plus 1, and 2x is the derivative of x squared plus 1. So this, using chain rule, let's remind us that this is the derivative of sine of negative cosine of x squared plus 1. All right, this is the derivative of cosines of x squared plus 1. Using chain rule, derivative of negative cosine x squared plus 1 equals to sine x squared plus 1 multiplied to 2x. So using this information, we can figure that the antiderivative of this function is negative cosine of x squared plus 1. Okay, so here plus and negative, I can just change this to negative. Plus and negative, I can just change this to negative. All right, and this is the antiderivative, and then you integrate it from 0 to pi over 4. So now you just need to plug this functions pi over 4 to this function and subtract 0 to this functions. That's going to give you pi over 4, right? So I want to simplify this as 2 over 3 pi over 4 raised to 3 over 2 minus 3. Cosine of pi over 4 should be square root of 2 over 2 minus arctan of pi over 4. I just keep it that way. You can evaluate, you can calculate this using your calculator, and pi over 4 squared plus 1 and minus cosine of pi over square, pi square over 16 plus 1 is going to be pi squared plus 16 over 16. So the green part is the is a value of big F, right? As I say, f of pi over 4 minus f of 0. Okay, so that's the value of big F. Of pi over 4, then now I just need to find the value of big F at 0. So minus, right? Minus 0 should be 0. Cosine of 0 is 1, so it's negative 3. Okay, arctan of 0 is 0, so cosine of 1 minus cosine of 1. So then this should be your answer for the definite integral of 0 to pi over 4 of this crazy function. All right, and there's an applications of the definite integral. Now we can consider the definite integral as the area of the regions. If you have a continuous function f of x, non-negative, so everything is above the x-axis, on a closed interval from a to b, then the area of the region bounded by the graph f, the x-axis, and the vertical lines x equals a, x equals b, is just equals to the definite integral of the function f of x from a to b. For an example, if you consider the regions bounded by the graph of this functions x squared negative x squared plus 4, the x-axis and the vertical lines from 0 to and 2 right here, right? This is the functions f of x equals to negative x squared plus 4. And then you can find this, and then the questions ask you to find this area right here, right? The area that is bound by this function's f of x, an x-axis, and this line x equals to 0, and then this line x equals to 2. So using this theorem here, you can figure this, the area here, so the shaded area here, and the shaded area here equals to the integral of the functions negative x squared plus 4 dx from 0 to 2. And look at the graph, right? You know that the function f of x is non-negative on this interval, so we can use this area function, area formula. And now it's simple enough. We just need to find antiderivative of negative x squared plus 4, which is negative x cubed over 3 plus 4x. And you integrate it from 0 to 2. And using fundamental theorem of calculus, you can just calculate the area. Negative 8 over 3 plus 8, right? And 0. So the answer should be 16 over 3. It's positive, makes sense, but area should be positive. And 16 over 3 is the area of this shaded area. And you can use this idea, right, to find the area that is bounds in between two functions. So for example, let's look at the function y equals 4 and the functions y equals 4 minus x. Okay, now I want to find the area in between these two functions. As you can see that the area in between these two functions is the same as the area under this curve right here, under the function y over 4, and then you subtract the area under this curve y equals 4 minus x. So the area, the red area here, right, the red area is the same as, so the red, right, I should have it red area equals to the area under the curve y equals to 4, so which is 4 from 0 to 4 dx minus the area under minus the green area. And the green area is the area under the curve of y equals to 4 minus x dx, right, from 0 to 4. And then we can combine these two together because we're looking at the same closed interval for, so 4 minus 4 plus x dx. So you have to 4x dx, and then you can find the antiderivative of x, which is x squared over 2 from 0 to 4, and then you would just plug 4 into x to get 16 over 2, which is 8, right? Using definite integrals, you can find the area here, the red area, right here. Okay, well, and if you want to make sure that using definite integrals to find area is a good way to do, you can calculate this area, the red area, using geometry. So this is a triangular, right? It's a right triangle. It's a right triangle, and the area of the right triangle is just the same as 1/2 of the base times height, and the base is 4, height is 4, so the area here, 1/2 of 4, right? The base is 4 and the height is 4, so it's just gonna be 8. Or this red area here is just 1/2 of this square, right? And 1/2 of the square is 1/2 of 4 times 4 is 8. So using geometry will help you clarify, or will help you check your answer when you use definite integrals to see if it's correct or not. All right, so this lecture introduces the idea of definite integrals. It is the integrations, right, antiderivative of a functions on a closed interval, and then the definite integral can be considered as the area under the curve of a non-positive functions that is bounds between the curve and the x-axis, and with the vertical lines. One starts as the lower bound of the definite integral, and another one is the upper bound of the definite integral.